Welcome back. So last lesson, we showed you an MRI machine or someone going into an MRI machine. This is the sort of output that they might have if they were having their brain scanned. An amazing amount of detail. The doctors can and clinicians can actually see various structures within the brain to help make some medical diagnoses. The great thing about MRI is that it's non-invasive. So the patient is not harmed at all in getting all of this data, but quite a revolution in innovation in technology. Okay, so in this lesson, we're going to look at low and high resolution proton nuclear magnetic resonance spectroscopy. So we're going to look at the principles of both low and high resolution NMR using proton NMR, and analysing spectra. Okay, principles of NMR. Remember from our last lesson that the 13-carbon nucleus contained 13 nucleons, 6 protons and 7 neutrons. In this case, we're talking about proton NMR, and the major isotope of hydrogen has a single proton in the nucleus, which means it's got an odd-numbered nuclei. In the presence of a strong magnetic field, the odd-numbered nuclei absorb radio waves and spin flip. And then when the nuclei flip from high energy to low energy, energy is released and recorded on an NMR spectrum, just as like it was for 13-carbon NMR. Okay, when we're looking at low-resolution proton NMR, we're looking for similar things that we were looking for 13-carbon NMR. We're reading the x-axis in chemical shift measured in ppm, starting from TMS, which again is our calibration point, and we're reading the peaks that appear from our reading right to left. So here we have 1, 2, 3 peaks. Sometimes a peak is shown for TMS, just look for that and don't include that as an actual peak. The number of peaks excluding TMS indicates the number of unique hydrogen environments in the organic molecule, and we can identify the type of hydrogen environment using our chemical shift values from the data book. So we do this in a very similar way that we interpreted 13-carbon NMR. Features of the spectrum. So the number of peaks, excluding TMS, is the number of non-equivalent proton environments. The chemical shift values correspond to the type of proton environment and use the data book for justification of assigning chemical environments. What's important in proton NMR is that the area under the curve, so this is the area under the curve, is proportional to the ratio of the number of protons in a particular environment. And sometimes you'll see, given on the trace, what we call integration curves, which is a way of measuring that area under the peak. And the integration curves, the relative height, tells us the ratio of hydrogens in that particular environment. So if the height is 6 centimetres compared to 4 centimetres compared to 2 centimetres, we've got a ratio of 3 to 2 to 1. So 6 divided by 2 is 3, 4 divided by 2 is 2, and 2 divided by 2 is 1. So that's the ratio of protons in that environment. Because you might need to use a ruler, always bring a ruler to your SACs and chem exams. Now, sometimes the areas are given instead of the integration. If that happens, then we can still determine the ratios to determine the number of protons in each unique proton environment. Okay, now we're going to look at principles of high-resolution proton NMR, and this gives extra information. So the features of the spectrum, similarly as with the other, the low-resolution proton and 13-carbon NMR, the number of peaks equals the number of non-equivalent environments, in this case non-equivalent proton environments. So excluding TMX, which is our calibration point. So we have 1, 2, 3 sets of peaks, so we have 3 proton environments. The chemical shift, according to the location on the x-axis, corresponds to the types of proton environments. And note that in proton NMR, the chemical shift range is less than in 13-carbon NMR, which goes up to about 200 part per million. The area under the curve, or the integration curve, is proportional to the ratio of the number of protons in that particular unique proton environment. But there's this extra special N+1 rule, which comes with high-resolution proton NMR. And you can see that here we have, this is what we call a singlet. It's the peak that doesn't have any further splitting. So this is a singlet here. But the second one is actually looks like AFL football posts, is actually what we call a quartet. That means next to the quartet, the carbon atoms next to the proton environment have 4 minus 1 equals 3 hydrogen neighbours. So we have hydrogen neighbours attached to adjacent carbons. Here for number 1, that's a triplet, and that means if we get 3 minus 1, we've got 2 neighbouring hydrogens on adjacent carbons. So the splitting pattern helps us piece the information about the molecule together. Okay, so when we're analysing proton spectra, we want to look for splitting. That tells us that we've got high resolution NMR. We also want to look at the chemical shifts and relate the chemical shifts to the data book, using for our justification the chemical shift range. So we could say that in this case, the hydrogens in this methyl are attached to this carbonyl group. The hydrogens in this group would have a chemical shift range of somewhere between 2.1 and 2.7 part per million. Remembering that we read the spectrum from the right to the left and we ignore the TMS, which is the calibration point. X in the data book stands for a halogen, so fluorine, chlorine, bromine, or iodine. Okay, a high-resolution proton NMR spectrum of an unknown compound has 3 single peaks, so no splitting, as shown. So this is peak 1, peak 2, peak 3. Identify 3 pieces of information about the unknown compound and indicate how each would assist in determining its structure. So we don't have a peak for TMS, so we know that we have 3 sets of peaks, indicates 3 non-equivalent hydrogen environments. Now, there are 4 options here. All we need to get the marks are 3 of these 4 dot points. There is no signal splitting, which indicates there are no regions in the molecule where hydrogen atoms are attached to adjacent carbon atoms. In other words, there's no neighbouring hydrogens. The peak area 3 to 3 to 2 indicates that the 3 hydrogen environments contain a ratio of 3 atoms to 3 atoms to 2 atoms of hydrogen, respectively. So a ratio of 3 could indicate a methyl group, and a ratio of 2 could indicate a CH2 group. The type of proton environments is indicated by the chemical shift. For example, using the data book, a chemical shift of 1.82 part per million indicates a CH with a double bond to another carbon, CH3, so protons in this environment. Or we could have said that the hydrogens in an OCH3 had a chemical shift corresponding to 3.53 part per million using the data book. So any 3 out of those 4 points gets the 3 marks. Okay, let's summarise what we've learnt, and we've learnt a lot in this lesson. So low resolution proton NMR shows the number of peaks is the number of non-equivalent proton environments, excluding TMS. The chemical shift corresponds to the types of proton environments, and for that you refer to the VCAR data book. The area under the curve, or the integration curve is proportional to the ratio of the number of protons in a particular environment. And in addition, high-resolution proton NMR, according to the N+1 rule, shows the number of splits in a peak is equal to the number of protons in the neighbouring proton environments plus 1. So these carbons have 2 neighbours. So this signal would be a triplet. This carbon has 3 hydrogen neighbours on an adjacent carbon. So N+1 would be a quartet split. And this carbon, no neighbouring hydrogens on an adjacent carbon. There is no adjacent carbon. So that will produce a singlet. Next up, we're looking at chromatography. I'll see you then. Bye.